At the end of this week, we finally actually meet and we can talk about root finding and the real deal with root finding. Yesterday's recorded lectures, we talked about the different techniques, we talked about the bracketing, and we talked about these open methods. Basically, Newton's method is almost definitely what you guys are going to be using. It's very prevalent in most cases because it has that nice quadratic convergence. I think I did mention in the lecture yesterday, the reason why the next step isn't used, Haley's method, is that calculating the third order is usually more complicated than just repeating Newton multiple times. So that's why that. What else is I going to say? Be careful looking up any information on Newton's method for root finding, because there's also Newton's method for optimization. And Newton's method for root finding is the function variable f divided by the Jacobian, the first derivative. Well, for optimization, it's the next one down, right? So it's going to be the first derivative divided by the second derivative. So if you go looking online for Newton's method, chances are you're going to find the one for optimization, which is different from the one for root finding. So just to be aware of that one. It's a bit of a pitfall, especially with some of the, because optimization is kind of like a generalization of root finding, then like a lot of the techniques that we're going to be talking about, line search and stuff like that, are usually attributed to optimization, but we still use them for root finding too. Okay, goals of today. I want to show you guys when Newton's method doesn't work, what we can do about it. General dimensional version, and I want to talk to you guys a little bit about line search algorithms for ways that we can improve convergence. Before we begin that though, I will just relay, we kind of missed the weekly discussion of how like AI has been useful for assignments and things like that. In the next like maybe a couple minutes, anybody have any experience with the last one? Yes. For people online, it's nice not to have to worry about plot syntax because Gemini actually gets that very, very nicely. Yeah, I agree. I also heard some feedback that it was pretty useless in a lot of the cases because the model, the question kind of required a bit more sideways thinking. When I tried it to develop the assignment in the first place, it actually came up with an error and the original code didn't work. Hence my little warning there, be careful about overlapping points for the boundary conditions. Hope you guys didn't run into the linear solver error. So, I mean, it's just kind of like a learning experience of how much you can actually use AI and how good it is versus, your understanding and having AI kind of fill in the gaps. Yes. Yes. Yes, 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 yes. Again, so the comment there was the big picture, it's kind of not so helpful anymore, but now as long as you partition it up and give it little chunks, then it's pretty useful. Okay, anybody else? Any other comments? Okay, so Newton-Raphson method. The last time we spoke about it, being yesterday on the recorded lecture, we found out that it amounts to basically finding using the current position, using the function value and its derivative to calculate the next increment. Graphically, I realized afterwards that I forgot to actually show you guys a graphic of what this looks like. It's very similar to the secant method, but now we're actually using the real tangent, not an approximation of that tangent. And because we have that information, we can get a better answer faster. Let's see. So yeah, so we start off at an initial guess. We go up, we find the tangent, follow it down, up, down, up, down, up, down. Good. Okay. Near the root, it converges quadratically, but there are some not so uncommon scenarios where it can fail, and it can fail pretty nasty. Newton-Raphson method only finds local roots and not all of them. So with the polynomial root finding, we can actually numerically find all of the roots necessarily. Newton-Raphson and any of these kind of methods, these iterative techniques, you're only finding the local one. And you really need that good initial guess. The nice thing is that at least in engineering, chances are you have a good initial guess, right? So my question here is, for example, if we want to solve a time-dependent temperature field in XYZ, three-dimensional, nonlinear, time-dependent, partial differential equation, what would our initial guess? So we're going to solve for T1 at time for 1 second, right? Given our initial value. It's an initial value problem. So we have temperature over the entire field at 0, time 0. We want to solve for time 1. What do you think the initial guess is going to be? Somebody give me an answer here. No? Come on. If you had to solve for the temperature field after 1 second, and you knew the temperature field in the beginning at 0 seconds, what should your initial guess be for the temperature field at 1 second be? Your initial field, right? This is time stepping. Because of stability reasons, we have to do this. It's called an implicit solve. We're going to have to use Newton's method to find like the next time step. And generally speaking, what we're going to be doing is just taking the previous time step as our initial guess. And chances are, as long as our time step isn't too big, spoiler alert, our time step shouldn't be too big, then we're going to get robust convergence. No problem. Okay. Here's an example of where things start to get funny. So here's a pretty straightforward polynomial, and we know going in that there is a root at negative 1.769, give or take. When we build our, yeah, okay. So the way this code works, we're defining our function, we're defining our derivative. A lot of computer packages now will be able to do symbolic logic. So a lot of the modern ones will handle that for you. This is not a modern symbolic logic package. This is bare bones stuff. So we actually have to write in our function. But that's actually a very useful feature because otherwise calculating Jacobian of some of these things can get super nasty. Yeah. We're defining this function. In general, you won't have to define a function for Newton-Raphson because it's a super standard tool, right? I wanted to show you guys what it looks like here because that way we can actually kind of pick it apart and see what it's doing at each step. Okay. So we start off with our initial guess. Where's my thing here? I had a little, oh no, that comes later, sorry. Okay, and then we're doing the Newton-Raphson and we're calculating x nu as x minus function value divided by the derivative, right? And we're chucking it on. Starting off at x naught equal to 5 and running it, and what we're going to do is we're going to plot the function and we're going to see the dots as they appear with the guesses. And what you get, it's already there, I should wipe the output, is no convergence at all. So what's happened here, our initial guess is over here, is 5. It's way up here. It's not even on the screen, but you can see the line there. It's jumped down to here, here, here. It's bouncing around here. It's not finding a root because it's not able to see there is a complex root there, where it's not able to see the complex root. So instead, this point here, the derivative is almost horizontal. And because you're dividing by horizontal, a horizontal derivative that's horizontal is 0 or near 0. So the next guess here shoots way the hell off and you're off to La La Land. You're like 3,000 or 4,000 in the wrong direction at this point, right? As opposed to starting off with a better initial guess, I think we started with 2 and there you go. So even though you still went through this little local minimum and you still went almost horizontal, you didn't go completely horizontal. And because of that, you can still find your solution and then find your root. So that's a good thing. There are even more funny cases like this guy, right? Square root of x, you would think that would be, well, what's the root of square root of x? Anybody? Where does a function square root of x become 0? 0? 0, right? No big deal. But it goes super khaki. This is a little bit cheating. Anybody know why this went so funny so quickly? Anybody? Class? Anybody? What's the problem with square root of x? You got it. Newton's method still can if you make it aware of complex numbers. The problem with complex numbers is that they're like complex numbers are kind of funny, right? A single complex number is actually 2 dimensions, is actually a 2-dimensional system. Hence, what we need to do is go in for n-dimensional Newton-Raphson, which we'll get to in a second. And it's actually really cool stuff. Stefan is here, right? Because he was interested in fractals. So I'm going to show him some cool stuff there. Okay. So we're going to come back to that complex one. Here are some other kind of common/uncommon failure situations. So this is a nice sigmoidal function. You see the desired root here, but because you're starting off here, you kind of jump around it and you actually end up getting farther and farther and farther, and you won't find it. Meanwhile, if you did start in here, then you would find it super quick because it's actually really easy. This one, you might find if the function has multiple roots, you're only going to find, no, you are going to find a root. You will not necessarily find the root that you are closest to. Big fallacy. I'll show you guys. It's super cool. Can't wait for that one. This is another problem. We kind of explored this one already. You jump, you can actually oscillate. Newton's method is known to be oscillatory sometimes. You start on one, you jump down, you jump back, and you can actually get caught in one of these loops, and you would never find your desired solution. Or you just so happen to find a place that the gradient is flat, and then you go off into La La Land because you're dividing by 0. These are simple cases because they're in 1D, so we can just look at the plot and think about it. When you get into ND, it gets a lot more insidious, I would say, because it's not always obvious that your gradient is 0 in one direction. And that becomes problematic because now you get into the situation where you've got this random function, not random, you've got this function, you've got one of your directions being flat, and that can cause a lot of problems. Okay, before we talk about mitigation strategies, let's talk about generalizing it to ND. So the ND Newton-Raphson method essentially is very, very similar. It generalizes very cleanly, except that you have to expand your notation a little bit. Okay? So given a system of n unknowns and n equations, we have a system of equations that we want to solve simultaneously. This should be like very familiar at this point, right? This is just a linear, this is a set system of equations. We did the linear ones, now we're doing the nonlinear ones. So what you get are n of these functions. You can generalize that. You can put that into a vector function, a vector function of vector arguments, which is a funny way to say you end up getting this system of equations. As long as, and the solution to those equations is when that system is equal to 0. In other words, we're looking for the roots. That's why the roots are important. Since we have n equations and n unknowns, it is conceivable that we will find a solution. We will not find the solution. We may not even find a solution, and no such solution may even exist. But there is a chance. There is a hope. Okay. The magic happens with the derivative. The derivative has to be a vectorial derivative, which is called the Jacobian in this case. I mentioned yesterday, be careful about considering this a gradient. Gradient is usually like the derivative of a scalar function by a vector. This is actually the Jacobian. It's the derivative of a vector by a vector. Because those vectors have the same dimension, being n, this becomes a matrix. And we can invert that. We don't even need to do pseudo-inverse. We can invert this plainly. Our Newton-Raphson method now becomes very similar, just we've generalized it to be the Jacobian here, right? So now it's the Jacobian times your increment vector is equal to your current residual, which is your f. What does this remind you of? J is a matrix. I'm going to go online. People online, be ready. All right. How about Nathan?
Sorry, I was not ready.
What does this remind you of? A vector times, a matrix times a vector is equal to another vector.
Linear system.
It's a linear system. Thank you. Right? So all of a sudden, all the things that we've been talking about previously, like when I said that linear systems are just all over the place and it's really the workhorse, it really is the workhorse. This is an example of computational thinking in that we've boiled down the more complicated general case of nonlinear system of equations back down to a series of linear equations for which we already have the tools. We've already understood how to do that. Okay, here's an example. Let's solve a system of nonlinear equations. This is super ugly, but we can still do it. By the way, paying attention, right? This is my warning. So you take these guys, you rearrange them so that sorry, typo. Rearrange them so that everything is equal to 0. Take all your constants, put them on one side, set them equal to your nonlinear function. Okay, you got that line, you got that line, you've got that line. Or in vector form, right? Your vector function is equal to this vector. And when it is equal to 0, i.e. when you've got a root, then you have solved your system of nonlinear equations. The Jacobian is very simply the derivatives, right? You can work this out by yourself. Derivative, 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 just fill it out. You can also ask, Gemini is pretty good at this, calculating the Jacobian. It's not perfect, so do check its work, but it's pretty good to get a quick answer. Otherwise, there's Mathematica, there's SymPy, there's Wolfram Alpha, there's 150 things, but honestly, these equations aren't hard to calculate the Jacobian for. Okay, and now given the Jacobian, we can solve for the increment. So let's see how it works. Function, we take a single value. Yep. Sorry, there was a typo on the sheet. Yeah. I'll update that right now. Save and okay. So if you give it a second and come on, give it a second and to reload, and it should update. Okay. So we define the function. Notice how the function is defined here. It's function of, it looks like a single argument, but that argument is actually a vector. So the first thing it does is break up that vector into its components, put together the equations, and then it returns it as a vector. So it's accepting a vector and it's spitting out a vector on the other side. Jacobian is doing the same thing, but now it's returning a matrix where it's just implemented directly. Okay, we've got our x is equal to x naught. That's our initial guess. And then we start the iteration process. This is just convenience. I had it spit out what the iterations were going to be and the norm of the residual. Note that we're not, in this case, we're not minimizing the norm of your f function. We're actually finding the root of all those f's, right? It's a difference from the least squares optimization. Okay, we can calculate the Jacobian, and now what? Nathan already gave us the answer. If we have the matrix, which is the Jacobian, and we have the vector, which is fx, how do we get Python to solve this? You answered lots of questions. Somebody else. Which one? Yeah. Direct solvers for the win. You can use anything, to be honest. It will commonly, especially once we start talking about numerical differentiation, which is kind of coming up next, then we're going to see that like the sparsity really kind of emerges. So generally speaking, you can use a sparse direct solver for this. This particular case is dense. Only in certain circumstances will these systems be symmetric, let alone symmetric positive definite, right? So just a warning on that one. Okay, And then we do the increment, we calculate the residual. If that residual, if the norm of the residual, let me take a step back again. Coming back to the idea of when we terminate Newton, there are the tolerances. One tolerance is when the step size, when the increment gets small enough, right? And that is useful because we've actually calculated for the increment. So we just take the norm of it. When it gets small, then we can cut it. The problem is that that doesn't actually solve your root. That just means that you've stagnated. It just means that you're not changing that increment fast enough. So it's not necessarily what you actually want to find. Alternately, you can look at the residual, right, which is just the norm of that f function, and say when that crosses a threshold. And again, you get into the argument of absolute tolerance versus relative tolerance. This particular case is an absolute tolerance, a relative tolerance, giving it our initial guess, 222. We have it solve, and here we go. Get a nice answer. Some nice properties with this. You'll notice that the residual is constantly decreasing, right? And remember, this is the norm of that vector. But the fact that it's always decreasing means that on our in this case 3-dimensional surface, we are constantly moving towards zero, which you would expect, right? You're following it downhill. Usually when you follow something downhill, you get to zero and you're decreasing along the way. All right, time to hammer home this initial guess thing. Let's start with a different initial guess. Now we're looking at 333. We still find the same root, which is a good thing. But if you look at the residual now, we start off with 30, 6, 1, 3, 5, 1, 0, 1, something minus 7, right? So now something has happened here because we've gone somehow from we're going downhill, and then all of a sudden we're going uphill again. And then we're going downhill again. So there's something funny going on here. But let's keep going. Let's try 10, 10, 10. And we also converge. This one, the residual is nicely decreasing, but we found a different root entirely. What if we try negative numbers? Minus 1, minus 1, minus 1. Right here again, we see something funny going on with the residual. And again, we find yet another root. Also kind of funny. And if we do something outlandish, like set one of these elements to 0, we actually have to run into our max iteration tolerance because our, oh no, look at that. It did actually find the root, but it took 53 iterations. And if you look at the residual here, you can see there's 1, there's 2, there's 23, 6, 2, 4, 48, 6. It's kind of doing one of these things. So the question is now, what is this? What does this mean, right? I'm kind of simple. I like to think in terms of 2 dimensions and being on a mountain, right? And it's a little bit funny that in stepping downhill, all of a sudden I'm over somewhere else. Okay? So we need to talk about basins of attraction. And basins of attractions are super awesome, and I'm glad I can finally show you guys this stuff. Okay. Depending on the initial guess, we arrive at different roots. Newton's method jumps around in the parameter space. So if you think about going down a mountain, right? Usually you're standing up on a hill, you want to reach the valley, you go downhill, but you don't just jump the entire way. You take little steps as you go down, right? So if all of a sudden there's a giant rock in the way, well, you turn around it and you walk down that way, right? Newton's method doesn't do that. It just says, well, I'm this high and I'm going an angle at that. I'm just going to teleport over there and just ignore everything else in the way. And if there just so happens to be a giant peak in the middle, doesn't matter, I'll just teleport straight through it. So what this defines is a something called basin hopping. When you move around between basins of attraction, so you're actually moving around between roots that you should be converging to. And this leads to kind of temperamental and a bit frenetic, but honestly really beautiful behavior. So temperamental but beautiful behavior. Let's look at, so first of all, Newton's method naturally handles complex numbers, like with this sort of thing, because now we're moving in 2-dimensional space and we've generalized it. Okay, let's look at this equation, seemingly simple equation, x cubed minus x What we're going to do is we're going to parameterize complex space, right? Real, imaginary. We're going to find, so first of all, how many roots does this equation have? Pop quiz, people at the back. 3, right? Third order differential equation, a third order equation, polynomial, not differential. You got 3 roots. What we're going to do is we're going to parameterize this. We're going to start and we're going to spam this thing. We're going to go with different initial values and see which of these 3 roots it lands in, and then color code it accordingly. Just as a heads up, when I first got Gemini to print this out, it started going through loops. So Gemini seems to be very bad with vectorization. Loops, it's very useful with. NumPy sucks with loops. So if you are doing this sort of thing and you want to get good resolution, like 500 by 500, you probably want to spend the extra time and eliminate all those loops. Even list comprehension is still pretty weak. Okay. That's what this code is doing. And live demo. Look at that. So these are different roots that it's converging to. And what do you think these guys are? Stefan, if you're online, what do you think these guys are?
They're fractals, sir.
They are fractals. That's right. This is a well-known behavior that generates fractals, which is really cool, but terrible, to be honest. It's really actually pretty bad for us. Even more impressive is this equation also has 3 roots. When you plot it, you get honestly beautiful stuff. It's beautiful, but terrible. If you guys are ever fans of Terry Pratchett, he was an English writer. He's like super prolific. He wrote something like 40 or 50 books, right? And his whole thing would be like, anything beautiful is terrible, and you should avoid it. Channeling my inner Sir Terry. What this means is that if you have an initial value, and granted this is for complex numbers, generally speaking, we're not going to be working with complex numbers, thankfully in this course, but if we're working with a situation where you have these bases of attractions and you're down anywhere near here, even the slightest change in your initial condition is going to converge to a completely different root. And the problem with that one is that the slightest change is a matter of round off error, and you will always have slightest changes. Always, always, always. So this is generally considered a bad thing. Although very beautiful, but we need to do something about it. So there are ways to modify Newton's method to achieve better convergence characteristics, excuse me. They cost more in terms of computation. They don't always work. And sometimes it's better just to do more iterations of Newton to get to the answer. So it's one of these magic games. The other thing is that when you are near a root, you want to use full-on Newton, because full-on Newton gives you quadratic convergence, which is the whole reason for using Newton in the first place. Okay. If we trust that delta x is giving us the right direction, all this discussion should seem very familiar because we've already talked about it in terms of iterating on roots for a linear equation. It's a little bit more complicated now because we don't have the same characteristics of that linear equation, so we need to be a bit smarter with this, but it's kind of similar, right? If we trust that delta x is pointing us in the right direction, we just want to make sure, walking down the mountain again, right? We want to take small steps. We don't want to magically teleport to the other side of a peak. That's how we're going to do it. So the easiest solution is literally to make it take small steps. Right? That's called the damped Newton-Raphson method. All you do, you actually keep your equations exactly the same, but now you're going to change your incremental update equation, multiplying it by a scalar, and that scalar is your damping constant, right? So for alpha is equal to 1, you recover Newton. Great, you want that around the root. When it's less than 1, then you are underdamped. In other words, you're taking smaller steps than you should. For over 1, you're overdamped, and now you're taking bigger steps than you should normally do. both of these are kind of meh, to be entirely honest. With the damped situation, with the underdamped situation, you end up converging very, very slowly, and it takes forever to do. Overdamped is terrible. What ends up happening is that you completely overshoot your route. So even in the region when you are close to your route and you should be converging quadratically, every time it wants to jump here, it jumps over here. And then it wants to jump there and it jumps over there. So you're literally like giving it a shove every time it wants to give you the right answer, which is bad. Okay. Or we could be a bit smarter with this and harken back to yesterday's lecture when we talk about route finding, except this time in the context of minimization. I know I'm getting into it backwards. Given the general idea of the damped approach that we have this scalar that we're multiplying by the direction, right? Again, we're talking about linear systems. What do we do with the linear systems? We optimized alpha, right? For the linear systems, that was pretty easy to do because we had those equations and they weren't changing, but we don't have them now. What we do have is a few pieces of information. We have the function value, the current function value. We have the slope, which is our Jacobian. And we have the full step, and we've probably evaluated the function at the full step too. We've got 3 pieces of information. And if we have 3 pieces of information, remember we're looking along a line, right? How would we find the optimal point if we have 3 pieces of information? What's an easy way to do that? Do you guys know what I mean? By the way, do you understand what I'm asking? Yeah. We have so we're over here. We want to know. We're over here. We know the slope is like. At least I'm not making any more arm movements. Okay. So we're over here. We know it looks like that. We've calculated what delta x is, and we've got, I don't know, something like that. Okay. How would we find if this is delta x here and we have our parameter alpha? How would we find the best guess that would give us the lowest residual? This is norm of f. Anybody? 3 pieces of information. What's that? That's 1. So that would be a midpoint. But we have one function value, we have the slope and the other function, and the other value over here. And given 3 pieces of information, what can we do with 3 pieces of information? We can fit it. What kind of function? Yeah. What kind of polynomial? Quadratic. Yeah. The quadratic with 3 pieces of information, we can fit the quadratic. Say it looks like that. There's our best guess. So instead of taking the full step, we just do straight to there, which is nice. That's one way to do it. Another way to do that is called backtracking. Backtracking is more of a mitigation strategy. So the idea is to improve the robustness of these steps by making sure that the function is well behaved in that area. So the idea with backtracking is you take that full step and then you say, okay, if this was the function value and this is the slope, I should get something down here, but I didn't. I got something up here. Something's funny. This isn't a good approximation, right? So what backtracking does is it starts to cut alpha. And it goes down, say it did something like this, right? And so it goes down and still not good enough. Okay, drop alpha a little bit more, getting better. Okay, that's the alpha that we actually take. So what it's doing is literally calculating backwards and trying to find a situation, an x, for which the function is still well approximated by that Jacobian. Yeah. And that's I've actually had pretty good success with backtracking. The alternative, personally, the alternative is some kind of bounded minimization. So this goes back to the bracketed case for root finding, but now we're looking at minimization. I apologize, I'm jumping all over the place here. It just goes to show like everything is kind of like using everything else. That's why it's kind of like hard about where you actually jump into this stuff. The other idea is that you have F over here, you have F over here, and you can do some kind of bracketed minimization in between. There are a few different, actually, there are a bunch of different ways to do this. I think NumPy or SciPy has something like 10 different algorithms for how you can use that information to best approximate where your next step should be. To be honest, whenever I get ambitious and I try and do this sort of thing, I usually just end up going back to Newton. Actually, I shouldn't say this. Maybe I should turn off the recording when I say this. My go-to personally, so I'm doing all this time-dependent differential equations. That's my bread and butter. If you take too big of a time step, then your previous guess is no longer a good guess for your next time step. And what that means is that the Newton solver starts to go all over the place. There are line search techniques, like we talked about, that will try and guarantee convergence. What I end up doing is actually just killing it after 10 iterations, cutting the time step, and throwing at it again. Which is a super like not good numerical way to do this sort of stuff, but for engineering practice, it works. Because what you can do, right? What you do is you say, solve for the next time step. If you fail for any reason whatsoever, cut the time step and try it again. Now you've got like one of these, have you guys done like error handling in programming stuff? Yeah, right. So like error handling is all about like generic errors and what you do with generic errors. Well, this is great because if I run out of memory, if I don't know, one of my RAM chips dies, if I have something else happening in the system, the model doesn't care. It just cuts it and tries it again.